This is Chapter 5, Torques and Moments of Force, Maintaining Equilibrium or Changing Angular Motion. The objectives of this chapter are to define torque, define static equilibrium, list the equations of static equilibrium, determine the resultant of two or more torques, determine if an object is in static equilibrium when the forces and torques acting on the object are known, determine an unknown force acting on an object if all the other forces and torques acting on the object are known and the object is in static equilibrium. Define center of gravity, excuse me, and estimate the location of center of gravity of an object or body. So this chapter is all about torques. Torques can cause change in angular motion. More specifically, the turning effect produced by a force is referred to as a torque. The torque produced by a force may also be called a moment of force or a moment. There are different types of external forces that may be applied. A centric force is a force exerted through the center of gravity. An eccentric, this is a type of force, not a muscular contraction, is an external force or not exerted through the center of gravity. The effect of an eccentric force is to cause change in linear and angular motions of an object. When applying a force to cause a rotation, the forces are equal but in opposite directions and often non-collinear. A pair of such forces is called a force couple. The effect of the force couple is to cause a change only in the angular motion of an object. The resultant of the two forces in a force couple is a force of zero. So according to Newton's first and second laws, no change in linear motion occurs. In general, then, a centric force will cause or tend to cause change in the linear motion of an object. An eccentric force will cause or tend to cause changes in linear and angular motions of an object. And a force couple will cause or tend to cause only change in the angular motion of an object. Golfing, hitting in volleyball, doing a power clean, rowing, and turns in ice skating are all examples of sports and sport positions that require torque for movement performance. The examples given so far are examples of external torques that act on the body or other objects. But what about within the body? What creates the turning effect that causes our limbs to rotate about our joints? Muscles create the torques that turn our limbs. A muscle creates a force that pulls on its point of attachment to the skeletal system when it contracts. When a muscle contracts, it creates a pulling force on limbs. Because the line of action of the muscle force is some distance away from the joint axis, a moment arm exists, and torques about the joint axis are produced by the muscle force on the limbs on either side of the joint where the muscle attaches. The torque produced by the muscle on the distal limb will tend to rotate the limb in one direction about an axis through the joint, and the torque produced by the muscle on the proximal limb will tend to rotate that limb in the opposite direction about the same axis. Consider the example of the torque produced by the elbow joint during flexion and extension. When the arm is in 90 degrees, the moment arm is largest, thus the amount of force that needs to be produced is lowered and the torque is greatest. However, when the arm moves closer to 100 degrees or more, or towards full extension, the moment arm decreases, thus a smaller torque. Therefore, during this movement, torque is variable and changes with the angle of the joint. Strength training exercises with free weights or weightlifting machines provide many examples of torques that are exerted on our limbs by non-muscular forces. To analyze the torques a weightlifting machine exerts on you, you must first identify the resistance force. Often cables or chains are used to redirect the line of action of the force of gravity acting on the weight stack. The direction of this cable indicates the line of action of the resistance force. We would then need to determine the moment arm by measuring the perpendicular distance between the line of action of force and the axis of rotation of the arm or cam of the device. Looking at the leg extension machine, the resistance force is provided by a stack of weights. This force is then transmitted to the arm of the machine via a cable attached to the middle of the arm. As the exercise is performed, the cable pulls on the machine arm. A torque is created about the axis of the machine arm because the cable pulls some distance away from this axis. As the exercise is performed, the line of action of the cable force changes, and the moment arm gets smaller as the leg reaches full extension at the knee. The resistance torque produced by this machine is thus largest at the starting position with the knee at 90 degrees and gets smaller as the leg extends. Torques that act around the same axis can be added or subtracted algebraically, just like forces that act in the same direction. For this example, imagine balancing a ruler on an eraser and placing a penny 5 inches to the left of the eraser. You would notice that the ruler no longer stays balanced and that the torque created by the eraser was 1 penny weight times 5 inches, or 5 penny inches of torque. The torque is positive because it tended to cause rotation of the ruler in the counterclockwise direction. Now if you were to place a penny on the right side of the ruler, 3 inches from the eraser, what is the net torque acting on the ruler about an axis through the eraser? To determine net torque, simply add the penny values. Thus, positive 5 penny inches plus negative 3 penny inches is equal to positive 2 penny inches. The net torque is still counterclockwise. If you were to place another penny at 2 inches to the right of the ruler, you would notice that the net torque would now be equal to 0. Therefore, the placement of the pennies resulted in static equilibrium of the ruler because the net torque acting on it is 0. Let's examine how the conditions for static equilibrium allow us to estimate the forces our muscles produce to lift or hold up objects. Suppose you are holding a 20-pound dumbbell in your hand and your elbow is flexed at 90 degrees so that your forearm is parallel to the floor. If the moment arm of this dumbbell is 12 inches about the elbow joint axis, what torque is created by this dumbbell about the elbow joint axis? Using the torque equation, we get torque is equal to negative 20 pounds times negative 12 inches, which is equal to positive 240 pounds. Therefore, the dumbbell creates a torque of 240 pounds in the counterclockwise direction. To hold up this dumbbell, your elbow flexors must create a clockwise torque equal to the counterclockwise torque created by the dumbbell. If the moment arm of these muscles is 1 inch, what force must they pull with to hold the dumbbell in the position described? Because the forearm must be in static equilibrium, the problem is solved as follows. The sum of the force times the moment arm is equal to negative 20 pounds times negative 12 inches plus the force of the moment times 1 inch is equal to approximately 240 pounds. So your elbow flexors must create a force of 240 pounds just to hold up a 20-pound dumbbell. What external forces act on a pole vaulter? So gravity pulls down on the vaulter with a force equal to his weight, and the pole exerts force on each of the vaulter's hands where he grips it. There are 2 other forces acting as well. There's 500 newtons acting on his left hand with a moment arm of 0.50 about his center of gravity. There's also a force of 1500 newtons acting on the vaulter's right hand with a moment arm of 1.0 meters about his center of gravity. Both of these forces creates a clockwise torque about the vaulter's center of gravity. Mathematically, the net torque about a transverse axis through the vaulter's center of gravity is equal to negative 500 newtons times 0.5 meters minus 1500 newtons times 1 meter, which is equal to approximately negative 1750 newton meters. The negative sign indicates that it acts in a clockwise direction. The 1750 newton meter net torque produces a turning effect that tends to rotate the vaulter clockwise onto his back, as if he were doing a backward somersault. If we were to continue analyzing the motion through the entire vault, we would see that the forces acting on the left and right hands would change and start creating a counterclockwise torque about the vaulter's center of gravity. The turning effect produced by the forces acting on the vaulter thus tends to rotate the vaulter counterclockwise in order to slow down the clockwise rotation and allow him or her to line up the body in preparation for clearing the bar. The center of gravity is the point in a body or system around which its mass or weight is evenly distributed or balanced and through which force of gravity acts. Most of the time, center of gravity and center of mass are used interchangeably. Center of mass is the point in a body or system of bodies at which, for certain purposes, the entire mass may be assumed to be concentrated. For bodies near Earth, this coincides with the center of gravity, thus they are used interchangeably. The center of gravity is an imaginary point in space. It is not a physical entity. Its location is not marked on an object. The center of gravity is a useful concept for analysis of human movement because it is the point at which the entire mass or weight of the body may be considered to be concentrated. So the force of gravity acts downward through this point. If a net external force acts on a body, the acceleration caused by this net force is the acceleration of the center of gravity. Looking at the human body, let's try to determine the location of center of gravity. Because your right and left halves are symmetrical, your center of gravity lies within the plane that divides your body into right and left halves, which is the mid-sagittal plane. Although your body is not symmetrical from front to back, the center of gravity lies within the plane that divides your body into front and back, which is the frontal plane. This plane passes approximately through your shoulder and hip joints and slightly in front of your ankle joints. The center of gravity location in these two dimensions is easy, front to back and side to side. The location of the center of gravity in the vertical dimension is more difficult to estimate. The center of gravity from top to bottom lies within a plane that passes horizontally through your body 1 to 2 inches below your navel, so this would be the transverse plane. This plane is slightly higher than half your standing height, about 55 to 57%. Women's tend to be lower due to a larger pelvic girdle and narrow shoulders. That's closer to 55%, while men's is a bit higher at 57%. Let's consider how limb movement may actually affect performance of a skill, affecting the center of gravity position. In a vertical jump and reach test, the objective is to jump and reach as high as possible with one hand. Self-experiment 5.8 in the textbook asks to try 3 different jumping techniques. 1, jump as high as possible, reaching with one hand while leaving the other at your side. 2, jump as high as possible, allowing both arms to reach overhead. And 3, jump as high as possible with both arms overhead and bring your knees up towards your chest. The center of gravity will move upward and any upward movement of a limb, or with any upward movement of a limb. However, during this experiment, the center of gravity stayed approximately the same location for all 3 jump types. The center of gravity movement is a relative movement. So in other words, raising your arms over your head causes your center of gravity to move higher relative to other body parts. For instance, your head. When you raise both of your arms over your head, your center of gravity moves closer to your head. In absolute terms, this could mean your center of gravity actually did move upward and higher off the ground, or 2, your center of gravity stayed the same height off the ground and your head and other body parts moved downward or closer to the ground to compensate for other body parts moving up. And 3, it could be a combination of these 2. Stability is the capacity of an object to return to equilibrium or to its original position after it has been displaced. Stability is affected by 3 things. 1, the height of the center of gravity. 2, the size of the base of support. And 3, the weight of the object. An object with a higher center of gravity is less stable. The base of support is the area within the lines connecting the outer perimeter of each of the points of support. An object with a greater or larger base of support is more stable, and an object that is heavier is more stable as well. Above are images of various stances and their corresponding bases of support, so you can see how different anatomical positions also correspond to different amounts of bases of